Imagine you have two numbers, like 2 and 5. An inequality is just a way to say which one is bigger or smaller. We use special symbols for this, the less than sign, which looks like a pointed arrowhead, the greater than sign, and versions with a little line underneath that mean, or equal to. The easiest way to see this is on a number line, a straight line where numbers sit in order. Smaller numbers are always to the left, and bigger numbers are always to the right. So if one number is left of another, it is smaller. If it's right, it is bigger. That's the whole idea. Why do we even need inequalities? Because in real life, things are rarely exactly equal. You might be taller than your friend, a phone might be cheaper than another, or a car might be faster. An inequality answers the simple question, how do these two amounts relate? Is one bigger, smaller, or the same? In math, this idea is the foundation for talking about ranges, like whole numbers bigger than 3, and for limits, where we care about values getting close to something but not quite reaching it. It's the first step from exact equality to the whole world of more or less. Now let's see the two big rules that make inequalities work. First, the trichotomy property. Trichotomy just means a cut into 3. For any two numbers, exactly one of three things is true: the first is less than the second, they are equal, or the first is greater than the second. On a number line, a point is either left of, right on, or right of another point. There's no fourth option. Second, the transitive property. If you know one number is smaller than a second, and that second is smaller than a third, then the first must be smaller than the third. It's like a chain: if a marble is left of a second marble, and that second is left of a third, then the first is definitely left of the third. The symbols themselves have a story. The less than and greater than signs come from a bent line with a stroke through it, originally meaning not equal. Let's solve a concrete everyday problem. Suppose the temperature in the morning is 15 degrees Celsius, and in the afternoon it's 22 degrees. Is the morning colder? We plot both numbers on a number line. 15 sits to the left of 22. Since left means smaller, 15 is less than 22. So yes, the morning is colder. We write this as 15 is less than 22. We can also say 22 is greater than 15. Now let's use the transitive property. If the night temperature was 10 degrees, we know 10 is less than 15, and we already have 15 is less than 22. So by the chain rule, 10 must be less than 22. The number line confirms it: 10 is left of 22. This same method works for any numbers. Plot them, and the left-right order tells you the inequality. You already know an inequality tells you which of two numbers is bigger, like a balance scale tipping one way. The golden rules are the moves you can do to both sides of an inequality that keep the tipping direction exactly the same. Think of the numbers sitting on a number line. Adding or subtracting the same amount just slides both numbers left or right together. The one that was ahead stays ahead. Multiplying or dividing by a positive number is like stretching or shrinking the whole number line evenly from 0. The gap between them changes, but the order never flips. These are the safe operations that let you solve for unknowns without breaking the inequality. Why do we need these rules? Because in calculus and physics, you constantly bump into inequalities, like finding where a function is positive, or how fast something must move. To answer those questions, you need to solve for a variable, just like you do with equations. The golden rules are your permission slip. They tell you exactly which algebra moves are safe. If you know x plus 3 is less than 10, you can subtract 3 from both sides and the inequality still holds. Without these rules, you'd be stuck guessing. They turn an inequality puzzle into a straightforward, step-by-step algebra problem. It's almost the same as solving an equation, with one extra twist we'll learn later about negatives. Let's see why these moves are safe, starting from something we know is true. Suppose we have two numbers, say 2 and 5, and we know 2 is less than 5. Now add 3 to both. On the number line, the 2 slides right to 5, and the 5 slides right to 8. The first point is still to the left of the second, the order didn't change. Subtraction is just sliding left, same idea. Now multiply both by a positive number, like 2. The 2 jumps to 4, the 5 jumps to 10. The gap doubled, but 4 is still left of 10. Multiplying by a positive is like zooming in or out on the number line from 0. Everything stretches or shrinks, but the left to right order is locked in. That's the deep reason these rules work. Let's use the addition rule in a real situation. Imagine two young trees in a park. Tree A is 2 meters tall, tree B is 3 meters tall. Clearly, tree B is taller. Both trees grow at the same steady rate, ½ meter per year. After 4 years, how much taller is tree B? We can write an inequality, 2 is less than 3. Each year, we add the same growth to both heights. Over 4 years, we're adding a total of 2 meters to each tree. So tree A becomes 2 plus 2, which is 4 meters. Tree B becomes 3 plus 2, which is 5 meters. The inequality still holds, 4 is less than 5. Adding the same growth preserved the order. Tree B stays taller by exactly the same 1 meter margin it started with. This same logic lets you solve any inequality where you add or subtract. Imagine you have two numbers on a number line, like 2 and 5. We know 2 is less than 5 because it sits to the left. Now, what happens if we multiply both by -1? The numbers become -2 and -5. But look at the number line, -2 is now to the right of -5. So the order has flipped, -2 is actually greater than -5. Multiplying by -1 is like reflecting the whole number line through 0, like a mirror. Everything that was on the left jumps to the right, and vice versa. This flip happens whenever you multiply or divide by any negative number, not just -1. This rule really matters because if you forget to flip the sign, your answer will be completely wrong. Think about solving a simple inequality like -x is greater than 3. To get x alone, you multiply both sides by -1. If you forget the flip, you'd say x is greater than -3. But let's test that. If x is 0, which is greater than -3, then -0 is 0, which is not greater than 3. So that answer fails. The correct answer is x is less than -3. This is the classic trapdoor in algebra. It's easy to miss, and it flips your entire solution upside down. Mastering this keeps you safe when solving real problems. Let's see exactly why this happens. Start with two numbers, say 3 and 7. On the number line, 3 is left of 7, so 3 is less than 7. If we multiply both by a positive number like 2, we get 6 and 14. 6 is still left of 14, so the inequality stays the same, 6 is less than 14. Multiplying by a positive just stretches the number line but keeps the order. Now multiply by -2 instead. We get -6 and -14. On the number line, -6 is now to the right of -14. The order has reversed, -6 is greater than -14. Why? Because multiplying by a negative is like a reflection through 0. The number that was smaller and further left becomes larger and further right after reflection. Dividing by a negative works exactly the same way because division is just multiplication by a fraction. Let's solve a real inequality step by step. Suppose you have -2x plus 5 is less than 11. First, subtract 5 from both sides to isolate the term with x. That gives negative 2x is less than 6. Now we need to get x alone by dividing both sides by negative 2. Here's the crucial moment. Since we're dividing by a negative number, we must flip the inequality sign. So negative 2x divided by negative 2 is x, and 6 divided by negative 2 is negative 3, but the less than sign becomes a greater than sign. The solution is x is greater than negative 3. Let's verify. Pick x equals 0, which is greater than negative 3. Plug it in. Negative 2 times 0 plus 5 is 5, and 5 is indeed less than 11. It works! Imagine you have a number, like 3. Squaring it means multiplying 3 by itself to get 9. The square root is the reverse question. What number, multiplied by itself, gives 9? That's 3. But what about negative 3? Negative 3 times negative 3 is also 9. So every positive number actually has two square roots, a positive one and a negative one. This is where absolute value comes in. The absolute value of a number is simply its distance from 0 on the number line, ignoring direction. So the absolute value of 3 is 3, and the absolute value of negative 3 is also 3. We write it with two vertical bars x. It's like asking how far, not which way. Here's the problem. You know from the golden rules that if you have an inequality like x is less than 2, you can multiply both sides by a positive number, say 3, and the inequality stays the same, 3x is less than 6. But what if you square both sides? Squaring is just multiplying a number by itself. The trap is that the number you're multiplying by could be negative. Remember the trapdoor, multiplying by a negative flips the inequality. So if x is negative, squaring it is like multiplying by a negative number, which can flip the relationship. For example, negative 5 is less than 2, but square them, 25 is not less than 4. The inequality broke because we lost the sign information. Absolute value is the tool that captures this. It lets us write rules for squaring and square roots that always work, by focusing on distance from 0, where sign doesn't matter. Let's build the rule from scratch. Think about the equation x squared equals 9. The solutions are x equals 3 and x equals negative 3. Notice that the positive square root of x squared gives you the absolute value of x. So we can write, the square root of x squared equals the absolute value of x. Now, suppose we have an inequality like x is less than 3. What does this mean? It means the distance from x to 0 is less than 3. On the number line, all such x must lie within 3 steps of 0. That means x can be any number between negative 3 and 3, but not including the endpoints. We write this as negative 3 is less than x is less than 3. This is the key rule. If x is less than c, then x is between negative c and c. It's just saying x is closer to 0 than c is. Let's solve a concrete problem. Suppose we need to find all numbers x such that x squared is less than 16. We can't just say x is less than 4, because negative 5 squared is 25, which is not less than 16, even though negative 5 is less than 4. Instead, we take the square root of both sides. The square root of x squared is the absolute value of x, and the square root of 16 is 4. So we get x is less than 4. Now we use our rule. This means the distance from x to 0 is less than 4. So x must be between negative 4 and 4. We write the solution as negative 4 is less than x is less than 4. Let's check. If x is 0, 0 squared is 0, which is less than 16. If x is 3, 9 is less than 16. If x is negative 3, 9 is also less than 16. The method works. You already know an inequality is like a balance scale that tips one way. Now we're going to solve two common types. A linear inequality has just plain x, like 2x plus 3 is greater than 7. A quadratic inequality has an x squared term, like x squared minus for x is less than 0. The big shift from solving equations is that the answer is almost never a single number. It's a whole range of numbers that make the statement true, like all numbers bigger than 2, or everything between 0 and 4. We show that range by shading a chunk of the number line. So instead of one dot, you get a colored stripe. Why do we care about ranges instead of single answers? Because in the real world, constraints are almost never exact. A bridge can hold any weight up to a limit, not just one exact weight. A projectile stays above a certain height for a whole stretch of time. In calculus, you'll constantly ask for which x values is this function positive, or where is the curve above the x-axis. That's exactly a quadratic inequality. The method we learn today, finding critical points and testing intervals with a sign chart, is the same tool you'll use later to figure out where a function is increasing or decreasing. It turns a messy inequality into a simple coloring-in problem on the number line. Let's build the method step by step. For a linear inequality like 2x plus 3 greater than 7, you already know the golden rules. Subtract 3 from both sides, the direction stays the same, giving 2x greater than 4. Divide by positive 2, the direction still stays, so x greater than 2. Done. The number line gets shaded from 2 to infinity. For a quadratic like x squared minus for x less than 0, we use a different trick because x is squared. First, bring everything to one side so it's compared to 0, it already is. Factor it into x times x minus 4. The roots, where this equals 0, are x equals 0 and x equals 4. These roots split the number line into 3 intervals, left of 0, between 0 and 4, and right of 4. Pick a test number in each interval, plug it into the factored expression, and just check the sign, positive or negative. Let's solve a concrete problem. Imagine you throw a ball straight up. Its height in meters after t seconds is given by negative 5t squared plus 20t. The question, for how long is the ball more than 15 meters above the ground? We set up the inequality, negative 5t squared plus 20t is greater than 15. First, bring 15 to the left side, negative 5t squared plus 20t minus 15 greater than 0. Divide everything by negative 5, and remember the trapdoor. Dividing by a negative flips the inequality sign. We get t squared minus for t plus 3 less than 0. Factor it, t minus 1 times t minus 3 less than 0. The critical points are t equals 1 and t equals 3. They split time into 3 intervals, before 1 second, between 1 and 3, and after 3 seconds. Test a value in each. At t equals 0, the product is positive 3, not less than 0. So far, we've compared numbers, like saying 5 is bigger than 3. Now we level up. We compare whole functions. A function is a machine that spits out a number for every x you feed it. So asking where is f of x greater than g of x means, for which x values does the first machine give a bigger output? Picture two curves drawn on the same graph. The inequality is true wherever the f curve sits strictly above the g curve. The answer isn't a single number anymore, it's a whole range of x values, an interval on the x-axis, where that above condition holds. We're finding the stretch of ground where one function dominates the other. Why bother comparing functions? Because it lets us trap a complicated, wiggly function between two simple, friendly ones. Think of a sandwich. The tricky function is the filling. We put a simple function above it, like the top slice of bread, and another simple function below it, the bottom slice. If we can prove the filling is always between the bread, and then we watch the two bread slices come together and meet at a single point, the filling has nowhere to go, it gets squeezed to that same point. This is the core idea of the squeeze theorem, a powerful tool you'll use in calculus to find limits of functions that seem impossible to grab directly. We're building the intuition now. How do we actually build these bounds? We start with a fact we know for sure. For example, the sine function always spits out a number between -1 and 1. That's its nature. Now we take our tricky function, say x squared times sine of 1 over x. Since sine is trapped, we can multiply that whole inequality by x squared, which is always non-negative. The inequality direction stays safe. This gives us a chain, negative x squared is less than or equal to our function, which is less than or equal to positive x squared. We've created an upper bound, the positive parabola, and a lower bound, the negative parabola. Our wiggly function is now in jail, between these two simple curves. Let's see the squeeze in action. Look at our trapped function, x squared sine of 1 over x, as x gets close to 0. The upper bound is the parabola x squared. The lower bound is the parabola negative x squared. As x approaches 0, both parabolas smoothly go to 0. They meet at the point 0, 0. Our wiggly function is forced to live between them. As the walls close in and the space between the bounds shrinks to nothing, the function has no choice but to also go to 0. We can say its limit as x approaches 0 is 0, even though the function itself is undefined right at 0. We found the limit by building a sandwich. This is the squeeze theorem, a gentle preview of a calculus superpower. We've spent this whole lesson learning the rules of inequalities on a number line. Now let's see why we bothered. Inequalities are not just abstract math, they are the language of real-world limits. Think of a factory making metal bolts. The design says the bolt must be 10 mm wide, but no machine is perfect. So the engineer sets a tolerance, the actual width must be between 9.8 and 10.2 mm. That's an inequality. Or imagine a highway with a minimum speed of 60 km per hour and a maximum of 80. That's a compound inequality. Or a business owner calculating how many cups of lemonade she must sell to cover her costs, that's a break-even inequality. In every case, we're not looking for one exact number, but a whole range of acceptable answers. Why do we care about bounding values? Because limits keep us safe and make things work. A bridge designed with a weight limit of 10 tons uses an inequality, the actual load must be less than that, or the bridge could collapse. A medicine dosage for a child is often bounded by weight, too little won't work, too much is dangerous. In business, a break-even point tells you the minimum sales to avoid losing money. Even the squeeze theorem you learned earlier is a powerful bounding idea. If a function is trapped between two others that both approach the same value, the trapped function must go there too. In every case, we're using inequalities to say this value must stay inside a safe or profitable zone. The process is always the same, and it uses everything you've already learned. First, translate the real-world limit into an inequality. A bolt width W must be within 0.2 mm of 10, so the distance from 10 is at most 0.2. Using absolute value, that's W, 10 at most 0.2. Second, solve it like any linear inequality. Split the absolute value into two, W, 10 at most 0.2 and W, 10 at least minus 0.2. Add 10 to all three parts, and you get 9.8 at most W at most 10.2. The golden rules of adding and subtracting work perfectly here. But what if the tolerance was on a cooling metal rod that shrinks? You might have a negative coefficient. That's when the trapdoor snaps. If you multiply or divide by a negative, you must flip the inequality sign. Finally, read the answer back into the real world. The machine must produce bolts between 9.8 and 10.2 millimeters wide. Let's solve a break-even problem from scratch. You start a lemonade stand. The setup cost, a table, cups, a sign, is $20. Each cup of lemonade costs you 50 cents to make. You sell each cup for $1.50. How many cups must you sell to make a profit? Profit means revenue is greater than cost. Revenue is 1.5 times the number of cups. C. Cost is 20 plus 0.5 times C. So we need 1.5 C 20 plus 0.5 C. Subtract 0.5 C from both sides. That's allowed, it's just adding a negative, no flip needed. We get 1 C20, so C20. You must sell more than 20 cups to break even. At 21 cups, revenue is $31.50, cost is $30.50, so you make $1 profit. Notice we never divided by a negative, so the sign never flipped. But if your cost per cup somehow decreased the more you made, a negative coefficient, you'd have to flip. That's the one rule to never forget.